Go ahead and start off by pausing the video and copying down these comparison notes on acids and bases. The stuff on the screen is the most basic of stuff for you to know. I can read it to you, and I'll go through some of the details, but there's a bunch of test questions over these basic differences between acids and bases, so be prepared for those. I do want to point out that acids are most generally identified by containing free-floating hydrogens, H+. All right. We're going to be referring to those as protons quite a bit in class today because it is just a floating positive, which is the same thing as a proton. Hydronium is the other compound that can be a general characteristic of any acid. And that is a new compound for you. H3O+ is called hydronium, and I've never showed that to you before. So make a note. You need to know that. On the base side, they have a different characteristic in regards to identifying a base, and it's hydroxide. That's not new to you. That's on your polyatomic list. But bases contain OH. Now, you'll see that I also list ammonia up there, and that's not like acids or H+, or sometimes H3O+. Ammonia is an example of a base that can trick you. All right? Bases most generally contain OH, hydroxide. Bless you. Now you're famous. Good job. Ammonia is another base, though, that, again, is new to you. So you need to know that NH3 is ammonia. I'm not going to get too much into the pH scale today. The pH has its own lesson on May 4th, so you do need to know going into your new assignments that acids have a pH value below 7, bases above 7, but we're going to go into great detail on the pH scale next week. Acids have a sour taste. Acids are found in almost all foods you eat contain acid, but most notably for the sour taste, where it's not diluted, is going to be in your stuff like fruits. So you do eat acids all the time, yes. Bases you eat far more rarely. You'll see that bases are commonly used in cleaning products, and they've got a real bitter taste to them. The only time that maybe in your childhood that you've had a lot of base that you've gotten to taste, maybe if your mom ever washed your mouth out with soap because you use such naughty language as most of you do. Acids have a sticky feel to them. If I were to pour hydrochloric acid on your hand when it was done burning, your hands would be sticky. And, of course, fruits have a sticky residue as well. Whereas bases have a slippery feel. Again, if you equate it to cleaning products, they've got that greasy, soapy feel that you are familiar with. You'll see there's some similarities on these lists as well, such as corrosiveness. Both acids and bases are corrosive, meaning they can cause damage to other items. You don't ever want to unfairly think that acids are dangerous and bases aren't. Sometimes that's a false notion that you have, because in a lot of our labs, I warn you, be careful of the acids. But bases are just as different, or just as different. Bases are just as dangerous. All right, a really, really strong acid is just as bad as a really, really strong base. All right, bleach is a reasonably strong base, and I promise if you just put your hand in bleach and leave it there, it'll burn you. We're going to talk quite a bit about indicators during the unit. We've got a lab on it in 2 days. Indicators are items that you can add to a solution or add to an unknown, and they change predictable colors based on whether or not they're containing free-floating hydrogens, acids, or hydroxides, bases. The general color scheme is here, but it works on the Roy G. Biv scale. So acids, by the way, those of y'all that are still writing while I'm talking, kudos to you. That's what's helping our test average go up. I know y'all had a good test, but hey, I'm saying important stuff. Have your writing utensil up. Acids are more towards the red side of the Roy G. Biv scale, while bases are more towards the violet side. Hey, based on that idea, if I told you a solution was neither an acid or a base, it was right in the middle, based on Roy G. Biv, what color would it be? Green. Roy G. Biv. Neutral solutions generally turn indicators green. Neutral comp. Acids and bases are both electrolytic. Now, I actually mentioned that when we did our light bulb lab, but at the time it didn't have much relevance because I hadn't done this lesson yet. But again, acids and bases are electrolytes. What was the other thing that was an electrolyte? Acids, bases, and anionic compounds. Thank you. So, in other words, if you add an acid or a base to a solution, it will help it conduct electricity. That's the definition of electrolyte. Solutes that help a solution conduct electricity. Water can be tricky. Water can act as both an acid or a base. You'll see that as we go through some of our vocab today, that while we most generally identify acids and bases based on whether they contain the H plus or the OH minus, sometimes we can get random compounds to act like acids and bases based on what they're doing with protons and stuff like that. So water is one of the examples of something that can be both an acid or a base, depending on the situation it's being put in. So you're going to want to make a note of that. So continuing on, I'm through this list now. Most of the other stuff will take place up here, but make sure you're writing important things that I'm saying. Another interesting fact, I want to bring your attention back to the activity series. It's the list that we once upon a time used when we did single replacement reactions. You don't have to get them out. I didn't make you memorize this list. I gave it to you on the test, so if I ask you questions about this one little fact that I'm going over, I'll provide you with the list. But what I want you to know is while acids and bases love to react together, that demo I showed you with the balloon, just an acid and a base immediately reacting together. Acids also like to react with metal. And the way you know whether or not it will is hydrogen is on your activity series here. Acids will react with metals that are above hydrogen on the activity series. Acids will react with metals that are above hydrogen on the activity series. So let's start to step into some of our fun vocab up here. The first big vocab word we're going to talk about is ARRENHIUS. We can have an ARRENHIUS acid or an ARRENHIUS base. You're going to want to draw everything I'm about to draw up here. The word ARRENHIUS is going to refer to the way that an acid or a base acts when it's added to water. Again, the word ARRENHIUS only deals with an aqueous setting. So the word ARRHENIUS is very specifically going to refer to the way an ARRHENIUS acid or an ARRHENIUS base acts when it's added to water. The other big vocab word we'll go into will be far more general to reacting with anything. But ARRHENIUS equals water, the aqueous setting. And I want to show you what each does. Here's an example of an acid. Hey, look at that guy, HNO3. How do I know he's acidic just by looking at him? Don't just say hydrogen, be more specific. It begins with hydrogen, all right? The majority of compounds, formulas, that start with hydrogen will be acidic. So here's an acid, and I'm going to add him into this water. An ARRHENIUS acid when added to water, is going to dissociate. We've done that word before. Dissociation is when the compound breaks into its parts with its respective charges. So when this happens, you're going to get nitrate ions, but more specifically for our focus is you're going to get hydrogen ions. And we know that when we're identifying an acid, that those H pluses are a major deal. So when an ARRENHIUS acid is added to water, you're going to get a bunch of free-floating hydrogens, which is a major contributor of it being acidic. There's another cool thing that happens, though. I want you to keep in mind that water is H2O. What do you think you would get if one of these free-floating hydrogens actually bonded to the water? Whoops, didn't mean H2, I meant H+. What would you get if you had one H to H2O? What would you end up with generally? H3O. Hey, not only would you end up with H3O, it added an H, but it also added a plus. Hey, what's the name of that thing we just created? Hydronium, which is the other main component that you can find of acid. And this is why both of them can be attributed to characteristics of acids, because when the ARRENHIUS acid goes in, you're going to get a bunch of those, and occasionally this will happen, which will give you possibly a bunch of those too. So what does the ARRENHIUS base do? Well, here's an example of a common base. That's sodium hydroxide, hydroxide being the big deal there. And let's put him in the water. And this is a little simpler. It's the same thing. You're going to get, in this example, some sodium ions that dissociate, but more specifically for our base study, you're going to get a bunch of hydroxides. And it's these guys that we're focused on for the base, for the ARRENHIUS base in water. The stronger the acid, the more H pluses. The weaker the acid, the less. The stronger the base, the more OHs. The weaker the base, the less. And if you're sitting there wondering, well, how do I know if the base is weak or strong? Look here. Here's a handout that you need. You'll see that this paper helps you in a couple ways. First off, it lists a bunch of acids and bases, so that can be helpful anyway. All right, but it lists the acids from strongest to weakest and the bases from weakest to strongest. There's a good reason it's like that. It's for the last topic of today's lesson. But you can find where the strong and weak acids and bases are if you just look at this location. So it can help you with general ideas on if it will produce a lot or a little bit of these ions, because again, the stronger the acid or base, the more H plus or OH minus it will produce. Let's move to another really big vocab word that kind of changes gears a little bit. It's called Bronsted-Lowry. You can have a Bronsted-Lowry acid, these are ditto marks, or a Bronsted-Lowry base. Ditto marks are a repeat of the word above it. Learn to use them to save your wrist in college. These definitions are really simple. It's the practice of them that's going to eat up the rest of our class time. A Bronsted-Lowry acid likes to donate protons. It'll be in the form of hydrogen, though. A Bronsted-Lowry base, instead of donating, likes to accept protons. Again, it'll be in the form of hydrogen. A Bronsted-Lowry acid is a proton donator. A Bronsted-Lowry base is a proton acceptor. And we're going to watch that happen to predict some products. So let's see this in action. Hey, look at this first guy here. Is he an acid or a base? How do you know he's an acid? It starts with H. So there we go. Here's our Bronsted-Lowry acid. Hey, what's he? How do you know he's a base?
Because
he's ammonia. So remember, ammonia is one of the new guys that you've learned. But before we continue, I want to point something out. All right, look here. Let's see how easy this is. We said that this guy was the acid. And acids want to donate a proton. To donate's like to give away. If you donate your toys are gone. So let's let this acid give away his proton, give away his hydrogen. Watch. It's gone. What's left? Chlorine. When he gave it away, all that was left was chlorine. But not only that, it's chlorine minus. And the way that I know that is, remember, I'm not just taking away an H. I'm taking away an H plus. And if I give away a plus, I'm left negative. Now, while the acid's giving the H away, it's not disappearing. Because what's the base doing? It's taking it. All right, so this H is moving from him and going to there. NH3, what will NH3 look like if it gains an H plus? NH4. NH4 what? Plus. All right, remember, it's carrying two characteristics with it, the H and the plus. All right, so this H moved to there, it became NH4, but there's a plus on it, and that's what? What's NH4 positive? You know that guy. Ammonia. You've learned him before. And that's it for now. We're going to add steps onto this, but we're going to practice this a little bit first. Let's try another. Question.
You don't put CO2
You don't, because of the charge.
Exactly.
Because it's an ion. Here we go. Write this down, please. All right, so we've got a new Bronsted-Lowry interaction here. All right. Hey, which one's easy to identify right away? What is the H2O? Yeah, here, we can get this acid really quick. All right. As we mentioned a moment ago, on your paper, the BR can be trickier. But the BR minus, we can get him to act like a Bronsted-Lowry base. And you can verify. Look on your base list. It's there. Now, let's remember what the definition is. The acid wants to give its H away. The base wants to accept it. There's the acid. Now, look, it's H2SO4. We're only giving away one H, guys. What will he look like if he gives away one H? HSO4. Not just HSO4, though. HSO4 negative, because he gave away a positive charge. All right, remember, it's a proton. So not only is he giving away an H, but he's giving away a plus. And if you give away your plus, you're left minus. Where's he giving it to the? He's giving it to the base. So what's going to happen if I add an H to BR? HBr. I'll answer that question. There is no charge on that HBr. Because if you look here, he was negative, and he gained a positive. All right? If you are negative, you're just sitting there negative, and then you gain one positive, guess what? You're neutral. Now, I was asked a question a moment ago. The question was, does that create two acids? The answer is no. It creates an acid and a base. And before that really throws you off, that's my last topic of the day. We're about to get there. It's called a conjugation. But before I show you why, I want you to practice one of these. See if you can answer this problem, this Bronsted-Lowry interaction, predict the products the exact way we did in the last two. You can pause. Now, careful of water because he can act as an acid or a base depending on the setting. But right away, I can identify this guy as an acid. So I know water will act as my Bronsted-Lowry base. I'm going to follow my rules that says the acid wants to give away an H while the base wants to gain one. If the acid gives away an H, I can see right there what's going to be left. Not only is it fluorine, but it's fluorine minus. Because it was neutral, gave away a plus, therefore is now minus. The base is going to accept that hydrogen. So while he used to be H2O, now he'll be H3O plus. All right, don't leave off that charge. He was neutral. He gained a positive. That will make him positive. Now let's take this a step further. I want you, this is the last step we're taking it today. Look back at your sheet. Now, when I give you this sheet on the test, it will not have the writing at the bottom. These are additional notes that I knew I didn't have time to make you write because we're going to get pushed up against the bell. So, you're going to want to rewrite these in your spiral eventually, not right now. Let's read what it says. The species that remains after a Bronsted-Lowry acid has given up a proton is the conjugate base of that acid. Look here. Let's see what that just said. It said that whichever one of these products is the leftovers of the acid is called the conjugate base. The leftovers. Okay, so let's look. Which one of these two guys is the leftover of him? The fluorine is. All right, that's what he started with. We got rid of the H, and there was my leftover. All right, so really, I could kind of connect these two guys together. All right, but you know, and it makes the conjugate base is what it's called. All right, now I want to see that you know that they're connected, and instead of drawing that stupid arrow, we're going to do it a way that makes more sense. I'm going to call this acid 1 and base 1. And that connects them together because they're both numbered 1. Again, this acid led to that base because this acid gave up an H and created that base. Now, it's true for the base as well. All right? A base will create a conjugate acid, which will be that guy over there. So there's an acid. But again, those arrows are annoying. This is not chemistry to draw these arrows. So instead of doing it, I'm going to keep using this number system. So there's my 1s, so we'll call the other ones my, this is base 2 and acid 2. And those numbers aren't giving them rank. All right, it's just connecting them into a group. All right, these guys are connected, they're the 1s. These guys are connected, they're the 2s. And they're conjugates of each other. Finally, these reactions can happen both directions. Bronsted-Lowry reactions are reversible. And they're going to happen more commonly in nature in one of the directions. And you can tell me which. What I'm saying is on the bottom. It's already printed. You don't have to write this. And not this second because you don't have enough time. But on that paper, it says that the reaction will occur towards the weaker acid. the reaction will occur in the direction of the weaker acid. And again, I have shown you where the strong and weak acids are. In other words, look here, look here. There's the two acids. Which one's weaker? Go find it. Which one of these two acids is listed on your sheet as being weaker? The answer is HF. Find it, verify. I want you to see that the HF is listed as being weaker than the H3O. Watch what I do. I want to show that the reaction is going to happen backwards more often than forwards. And here's how you do it. This shows that the reaction will happen both directions, but it favors backwards. Because the weaker acid is that direction. And that's just what happens in nature. Let's do another one of these so we can catch up. I know that that last pill is kind of tough for some of y'all to swallow. It's just going to take practice to get good at it. Let's do one more before we call it a day. Write this down, please. Now, draw your arrow lightly because remember, we're going to redraw that arrow to show which side is being favored. Hey, which one of these compounds can we identify very quickly? Yeah, I see an acid. All right, starts with H. I know, but we've got to be aware of water. All right, tread lightly with water so you don't drown. They won't be. And here's our Bronsted-Lowry base. So let's follow our steps. We know that the acid wants to get rid of his H. If I get rid of his H, what am I left with? ClO4. ClO4 minus. Where does that H go?
To the base.
Over to the base. H3O plus.
So if you get base acid, base acid. Yep. You didn't say that. Acid, base acid.
Now we want to identify the conjugates. So I could call this one base 1, and I could call this acid 2 just to start setting up my groups. All right? And I'm going to have a 1 over there and a 2 over there somewhere. So let's see where each one came from. Look at that guy. Did he come from the acid or the base? He's the leftover of the acid. So this will be the conjugate base 2, which puts them together. That's the conjugate base of my acid. The hydronium was a modified version of the water. So I will say that they are connected together, and this is the conjugate acid. Questions on what I just did right there, because that's usually where some of you get angry at me. I'm going to erase this arrow, and I want all of you to silently draw the 2 arrows the correct way. Draw the arrows the way that they will show this reversible reaction. So Gabriel, the acids, there's 2 acids, yeah? I'm telling you that the bigger arrow needs to point towards the weaker acid. Will this acid be, I'm sorry, will this reaction be forwards or backwards most often? Forwards. Forwards. So you're comparing H3O to HClO4.
I know now.
One last thing, I skipped something, so now I'm with an empty room, but you're watching. So, two last vocab words that we are supposed to hit is monoprotic acids versus polyprotic. And it's actually a good one for me to have skipped because it's the easiest one. But you can identify these based solely off the number of hydrogens in your acid. So monoprotic acids have one hydrogen, while polyprotic acids have more than one hydrogen. So if you look back at your earlier examples from this lecture, you'll see that our very first example or acid that we used was hydrochloric acid. He only had one hydrogen, therefore the HCl is monoprotic. Whereas in our second example, we used sulfuric acid, which was H2SO4, which would be polyprotic. You could call them diprotic since there's two, but polyprotic, an acid with more than one hydrogen.